Hi, so in this video we're going to look at rolling down inclines, and in particular we're going to look at how energy gets divided when an object rolls down an incline. So let's kind of make it our goal to do the following. Let's say that we have an object at the top of a ramp. Let's say that it has 10 joules of gravitational potential energy at the top of the ramp. And then we let it roll down the ramp. When it gets to the bottom, the center of mass is going to be moving with some velocity. So that's going to give it a translational kinetic energy. Also, the object is going to be rolling, so it's going to have some omega, and it's going to have, therefore, some kind of rotational kinetic energy. So, like, the question would be, of these 10 joules that we start with, right, how many of them go into rotation, and how many of them go into translation? We know that they've got to add up to 10, but what we want to know is, how do they split up? How does that 10 joules split up? That's what the goal is, okay? So let's see if we can work out the physics of this. So what we're going to do with this is we're going to write down energy conservation, and we're going to say that the GPE at the top of the ramp is going to be equal to the sum of the kinetic energy translational plus kinetic energy rotational at the bottom of the ramp. So guys, this is energy conservation, right? Potential energy in one place, top of the ramp, equals kinetic energies at the bottom. And there are two now that we have to worry about. Okay, so how do we proceed from this point? What we're going to have to do is we're going to have to remember something that we came up with in class. We're going to have to remember that if you have an object which is rolling, and it has a certain shape factor, c, right? We said that, let me put recall. Recall that we said that the ratio of rotation to translation kinetic energies is equal to the shape factor, okay? That's something that we showed in class in kind of a separate derivation, but it's a really important result, okay? That the rotational kinetic energy divided by the translational is going to always be equal to the shape factor of the object. That's super important. Remember that the shape factor is greater than 0, and it's less than or equal to 1. And it depends on how mass is distributed in the shape. So we said for a hoop, the shape factor is 1. But for a disk or for solid objects, the shape factor is less. So that shape factor tells you something about the rotational inertia of the object. All right, so let's use this, and we're going to actually use this relationship and rearrange it. And we're just going to use it, and we're going to solve for the K Irrotational. The reason we're going to do that is because we're going to actually stick it in, and we're going to get rid of it up in the top, so that we get an expression that only has KET in it. So now let me go back and let me write this. So now the GPE is equal to KET plus C times KET, right? We just did our substitution right there. And the nice thing about that is that now you can factor out KET. Okay, so remember by algebra, there's an implied 1 here. Of course, there's a C there. And so you factor out and you get this 1 plus C. I'm going to leave the math to you, but I hope you can see that if I divide both sides by the GPE, then the GPE comes over on the right side. But then I'm going to divide both sides by 1 plus C, and that puts that over there on the left. This actually gives us one of the things we were looking for. All right, this tells us how much translational energy we have as a ratio of the total gravitational potential energy that we started with. Okay. Now, before I talk about the physics of that, let's get the other ratio. Let's get the Ke rotation divided by GPE, and then we can talk the physics. Okay. So if we were to do this, start over again. Let's do our substitutions again, except now I want to substitute for Ke translational. Now I want to get rid of this, and I will allow you to check this, but using the same relationship up here, we're now going to kick out the KET and replace it with this. And then plus KER. You see what we did? This term right here actually is replacing Ke translational. Okay. So now we've got a little more complicated algebra here. We can factor out the Ke rotational. It's going to factor out as 1 over C plus 1. It's kind of a pain. That's the same thing as 1 plus C over C. Right? And so the ratio that we're going to end up with, I'm going to have to write this on the side here. Let me just go down. The ratio that we'll end up with is going to be this one. Okay, so you can check my algebra there, but basically you're just cross-multiplying stuff to move it over. And what you end up with here is your second relationship that complements the first one. These two relationships make up a pair, right? And they tell us how the energy would split. And apparently the energy depends on the value of C that we have for the shape. Okay. Yeah, so let's go back to our original example, and let's just see how that would work here. So if I want to know how much rotational energy I have, I would take rotational divided by 10 joules. That's going to be equal to C over 1 plus C. If I want to know about translational, out of 10 joules, I would do 1 over 1 plus C. Right? So I'm just using those two box formulas. Now we got to pick a shape, right? We have to pick a shape. So why don't we say that C is equal to I don't know. Let's make it 1/2. That's for a solid disk. Right? We're going to commit to that shape now. So what we're going to have here would be 1/2 over 1 plus 1/2. So that's 1/2 over 3/2, 1/3. Okay, you can check the math on that. The 2's cancel, leave you with a 1/3. If you do the math over here, you would get, for translation, 1 over 1 plus 1/2. That's 1 over 3/2. That's equal to 2/3. And the first thing I like about this is that I can see that 1/3 and 2/3, they both add to give me 1, which means that's good, okay? Because these are fractions, right? And the fractions have to add up to the whole in this case. So how much energy are we going to have here, right? How much rotational kinetic energy are we going to have if rotation over 10 is 1/3? And the answer is if you take that 10 and move it over here, is that you're going to have about 3.3 joules of rotational kinetic energy. So our answer for this is 3.3 joules. If you look at translation over 10 is equal to 2/3, right? So you multiply 2/3 times 10, and that's going to give you, what, 6.7? And that tells you over here that this is 6.7. And so now I know exactly where my 10 joules went. I know that 3.3 went into rotating the object, and 6.7 went into actually having it have some type of translational energy. Okay? So the ratios, the formulas, to kind of summarize here, the formulas that we came up with on this other page, these are nice because they tell you exactly how the energy splits up. Also, they depend on C. So you need to know what the shape factor is. That's really important. You have to know what it is, and it's going to change for different shape factors. And the last thing I'll ask you to think about is, if you pick shapes which have their mass distributed near the edges, shapes that have big C values, I hope you can see what the effect is going to be, especially if you look at this equation. If I make C very big in this equation, what's going to happen is this whole fraction gets small. And that means I have less translational kinetic energy. So the more that you push mass away from the axis, the less translational energy you have, and the more rotational energy you're going to have. And you can see that in this equation. By increasing C, you make the rotational energy greater. So there's some physics for you to think about as you work on your problem set. But hopefully this will get you started with those. Okay. Good luck.